Well, I hope we're doing well. This is the last video for integrating by partial fractions. And if you're looking at this, you're going, but that's not polynomial. And you're right. And actually, it's one of those things where we're going to use u substitution, then decompose into partial fractions, then integrate, then substitute back in for u. And it winds up, you're like, wow, that's a whole lot of work. But actually, this one winds up being really straightforward. So if we let u equal to sine x, then of course remember that du becomes cosine x dx. We can use partial fractions to basically break this into something that is integrable, because when we do that, we get du over u plus u squared, which then of course factors into u and 1 plus u. And so basically what I'm doing is I'm just going to be doing my partial fractions with u, with linears of u instead of linears of x. Well, I'm sure you pretty much figured out that this one's going to be so easy. Let's go ahead and let u equal to 0. If u is equal to 0, let's go ahead and, a u plus 1 plus u and b times u. If u is equal to 0, you get 1 plus a times 1. A is equal to a times 1, so a is equal to 1. And if we let u equal to -1, we're still going to get 1 over here on this left side, but we're going to get b times -1, so b is equal to -1. Well, that means that my integral of du over u times 1 plus u can be rewritten as the integral of du over u, right, because a was just 1, minus the integral of du over 1 plus u, because b was just -1. Well, that winds up integrating really easily. So natural log of the absolute value of u minus the natural log of the absolute value of 1 plus u plus c, but it wasn't in terms of u to begin with, so I have the natural log of sine x minus the natural log of 1 plus sine x. And by the way, you can leave it like this, but remember that by properties of logarithms, this could be rewritten as sine x over 1 plus sine x, plot those absolute value bars, and this, winds up being a little bit simpler, but this, of course, is legitimate as well. And so, if you look at something that actually isn't polynomial, but the denominator necessarily factors, and it's in a form that isn't really helpful to you right now, then yeah, you should go ahead and at least try to do u sub, and then from the u sub form, you can decompose into partial fractions, use those partial fractions to integrate, and then come right back to where you are. And right back into the original variable. So bonus, let's do this again, but let's do it with e this time. What do you say? Now, what we need to do here, and in this case, it's little more than just cleaning it up, right? So if we let u equal e to the x, and then remember that makes du equal to e to the x dx, so really that becomes du u minus 1 and u plus 4. And the thing is that is really easy to see inside of that. It just, like I said, kind of like regular u sub problems. It, could you possibly do the decomposition just leaving it with e to the x? Probably, but it's just a little bit cleaner doing it this way. So u minus 1 and u plus 4. That makes a over u minus 1 plus b over u plus 4, and you get 1 is equal to a times u plus 4 and b times u minus 1. Now let's go ahead and use our convenient values by the Heaviside method. Let u is equal to 1, and if u is equal to 1, then I get 1 is equal to a times 5. And if I let u equal to -4, I'm going to get 1 is equal to b times -5. So a is equal to 1/5, and b is equal to negative 1/5. So what happens here is I wind up with 1/5, or d, let's call it 1 over u minus 1, and 1 over u plus 4. And that, of course, becomes 1/5 du over u minus 1, and 1/5. Oh, so that's supposed to be negative, right? This right here should be negative, so that should actually be a minus sign because b was negative. Sorry about that. Little snafu. U plus 4. Now from here, the integration is really easy. I have 1/5 natural log absolute value of u minus 1 minus 1/5 the natural log absolute value of u plus 4 plus c, and then now I simply have to plug back in. And now that first argument needs the absolute values, because think about e to the x minus 1, right? E to the x is always positive, but e to the x minus 1 actually has the possibility of being negative, and actually is negative for x being, for when x is negative, right? But this next one, because it's e to the x plus 4, actually doesn't need absolute value bars anymore, and there we go. Now, that was relatively easy. Let's do a hard one. Alrighty, this one now. Now we have one, does this factor? Well, yeah, it factors, because what we have here is we have dx over, and this is x to the 1/2, and this is x to the 1/3, but if we get a common denominator, that's x to the 3/6 minus x to the 2/6. Okay, well, just for giggles, let's try setting u equal to x to the 1/6. And if we do that, then du is equal to 1/6 x to the negative 5/6 dx. And you're like, yeah, that's pretty interesting, Mr. Forth, but that expression right there is not in the integrand. Okay, well, let's play around with this a little bit. We can go ahead and make dx equal to 6x to the 5/6 du. And since x to the 1/6 is u, that becomes 6u to the 5th du is equal to dx. Okay, so this winds up being my substitution for dx. This winds up being my substitution for x to the 1/6. So I wind up rewriting it as 6u to the 5th du, because that's my dx, oddly enough. And I wind up getting u cubed minus u squared. Now, thankfully, this actually reduces a little bit, right? Let's pull the 6 out in front, and this becomes u cubed du over u minus 1. Well, that's still a little bit messy, and I actually don't wind up having to, when I do the substitution in this way, I don't wind up having to do any partial fraction work, but I do have to do some division. And you know, you could take u minus 1 and divide it into u cubed, or you could recognize that u cubed is the same thing as u cubed minus 1 plus 1. And since I just don't like doing division, like polynomial long division, let's go ahead and pull this apart into u cubed minus 1 over u minus 1 plus 1 over u minus 1 du. And that, of course, gives me x squared, or sorry, not x. Let's go ahead and start over on the next line since I messed up the variable. We wind up getting u squared plus u plus 1 plus 1 over u minus 1 du. Whew. Now, this looks nothing like that, okay? But we have used substitution in order to transform a rational expression. And I think this was in this section because if you do the substitution in a little different way, you actually do get a denominator that is factorable. And this denominator was factorable, but it was also cancelable with what came above it. Now, when this happens, what we need 6 1/3 u cubed 1/2 u squared plus u plus the natural log of u minus 1, all of that plus c. Now, because let's go ahead and distribute the 6, and we're going to get 2u cubed plus 3u squared plus 6u plus 6 natural log u minus 1 plus c. And now let's substitute back in, and we're going to get 2, and this is x to the 1/6 to the third, so x to the 3/6 or x to the 1/2. When I square u to the 1/6 squared is u to the 2/6, or x to the 1/6. X to the 1/6 squared is x to the 2/6, so x to the 1/3 when it reduces. And this becomes 6x to the 1/6 plus 6 natural log x to the 1/6 minus 1 plus c. And you're thinking to yourself, that can't possibly be correct. It actually is. Okay, and go ahead and do the work yourself. I'm not going to do it right here. Largely, well, I tell you what, there's time. I'm going to show you that this, when I differentiate, leads me right back to this. Are you ready? This is going to be fun. Okay. Let's go ahead and just take the derivative of this. I'm not going to rewrite it. I'm just going to take the derivative. That winds up being, coefficient comes along for the ride, and the derivative of x to the 1/2 is 1/2 x to the negative 1/2. The 3 comes along for the ride, and it's 1/3 x to the negative 2/3. The 6 comes along for the ride, and it's 1/6 x to the negative 5/6. And of course, we're going to get 6 times 1/6 x to the negative 5/6 over x to the 1/6 minus 1. And you're skeptical, I can tell, but I'm going to show you. Now, of course, the 2 and the 1/2 cancel. The 3 and the 1/3 cancel. The 6 and the 1/6 cancel. And what I'm left with is 1 over x to the 1/2. But I'm going to go ahead and call it x to the 3/6. Now, this winds up being 1 over x to the 2/3, but I'm going to call it x to the 4/6. 4/6. This is going to be 1 over x to the 5/6, and this 6 and this 1/6 cancel. This is going to be x to the 5/6 times x to the 1/6 minus 1. And now I need to get a common denominator. And you're thinking, surely you wouldn't do that. Well, yeah, I'm going to do that. Okay. So in order to get a common denominator, I need to figure out what factors are missing from each that are in another. Now, x by itself, the largest that it ever gets is x to the 5/6. And therefore, I need x to the 2/6 to be multiplied by this one. But I also need this binomial, and I get x to the 1/6 minus 1 over x to the 1/6 minus 1. So that ought to take care of that first term. Similarly, with the second term, I'm going to get x to the 1/6, x to the 1/6, x to the 1/6 minus 1, x to the 1/6 minus 1. Now this next one is nice because I have as many of the x's. I simply don't have the binomial. And then, of course, the last term has everything that all of the others have and more. Alrighty. Now, the denominators are all going to be the same, obviously. And so x to the 2/6 distributed across here becomes x to the 1/2 minus x to the 1/3. X to the 1/6 distributed across here becomes x to the 1/3 minus x to the 1/6. And I guess you see where this is going. This is positive x to the 1/6 minus 1 plus 1 all of that over x to the 5/6 times x to the 1/6 minus 1. This cancels with this cancels with this cancels with this, and what I'm left with is x to the 3/6 over x to the 5/6, x to the 1/6 minus 1. Now this can reduce, and I'm left with 1 over x to the 2/6 down here, 2/6, x to the 1/6 minus 1. And then when I distribute, it's going to be x to the 3/6 minus x to the 2/6, which is x to the 1/2 minus x to the 1/3, which is the square root of x minus the cube root of x. And let's go back to the original integrand. That is exactly what the integrand was. Messy, right? But the reason why it actually worked out is these just sort of canceled out and only left that x to the 1/2 out in front. All right, so that was fun. Always good to check your answers, and it was worth a couple of minutes, I think. This brings our discussion of integrating by partial fractions to a close. In the next couple of days, we'll be dealing with integration strategies, and I will start work on some videos that actually help us to walk through some of those things and strategize which methods that we've appropriated in this chapter, and of course U-sub from earlier chapter, in order to figure out how best to attack integrals when we're faced with them and not given a specified method. Okay. Yeah, if you have any questions, shoot me an email. Bye.